Okay, so good afternoon. Should we start? Then the situation we had is we were assuming we have a function d with all these properties, and then we wanted to prove that it is the cost function associated with some production function. And we proposed a candidate. So we define the function f by f of x equal to the maximum of y and plus such that d of yp is less than or equal to px for every p. And we saw that this function is well defined and very nice. It's quasi-concave, non-decreasing, and upper semi-continuous. But now we want to see that the cost function induced by this production function is precisely d. Okay, so let's define the cost function associated with f . And let's compare it with d. We will see that it is d. Okay? Now, for every x satisfying this inequality, because y, f of x is the maximum y satisfying this condition. And this y is smaller than the maximum. Because we saw that the y satisfying that condition are an interval of the type 0 f of x, then this y satisfies this condition. Okay? So, is this clear? No? Okay. So I fix y and x satisfying this inequality. Look at the definition of f of x. It's the maximum y satisfying all this. But how is the set of those y's satisfying all this? We said that it's a closed interval of the type, is actually the interval 0 f of x. Okay? Is this clear or not? No, it is. Then if you don't agree, I will do my best to convince you. Okay? So, first of all, you accepted that it's a maximum, so it's a real number. Okay? So I'm sure you agree that if y I mean, I consider the set of y's satisfying none of these. So let y be, x is fixed. Let y be such that all these conditions hold. Okay, then y is less than or equal to the maximum f of x. But if I take a smaller y, because d is non-decreasing, dy prime of p will also satisfy all these conditions, which means that y prime I'm considering the set of y satisfying this. And this is the maximum. F of x is the maximum y. But I say every number smaller than f of x satisfies this condition. So this means that the set of y's of this type is of the type 0 f of x. Okay? Yes or no? Hmm? Yeah. Any y satisfying this condition lies in the interval. And if y does not lie in this interval, does not satisfy this condition because it is greater than the maximum y that satisfies this condition. Okay, so this is an interval, 0 f of x. And I hear one of those y's in this interval. Then it satisfies all these conditions. That was the argument. And what does it say about the cost function c? C of yp. Look at the definition of c of yp. Is the minimum px under this constraint. And we have just seen that every x satisfying this constraint has that for every p we have this inequality. So for the minimum p, which is the cost, we will have this inequality. Okay, so we have that c of yp is greater than or equal to d of yp. And this is true for every y and every p in R plus plus n. We want to prove that c equals d. Well, we have already got something, that c is greater than or equal to d everywhere. Now, d of yp is smaller than this number and is non-negative. Okay, look at the definition of d. And then d of yp is a real number. That's obvious. But look at this condition. This condition says that if this is finite for some p, this is finite for every p. It's always finite or always plus infinity. So if one time is finite, it's always finite. So this means that this function is finite valued everywhere. And it is a concave function because we are assuming that it's, we are assuming that it's superlinear. Superlinear is concave plus linearly homogeneous, positively homogeneous of degree 1. So it is concave. Change the sign if you want. We have a convex function, finite valued everywhere. So every point is in the interior of its effective domain, because its effective domain is the whole of the space, R plus plus n in this case. Okay? So I can take a subgradient. The subdifferential is non-empty. We proved that. Well, but here we are dealing with concave. So what exists in this case is a supergradient. We have to reverse the inequality. So the conclusion is that the subdifferential of this function at P is non-empty. Then we are going to take a point superdifferential. Okay? Let's write delta bar to distinguish superdifferential from subdifferential. It is non-empty, so let's take an element here. What is the meaning of being a supergradient at P? The meaning is that for every Q, for every other P, say it Q, D of YQ, then the supergradient inequality with subgradient it was greater than or equal to, with supergradient is less than or equal to. D of Yp plus Q minus P inner product Z. Inner product is symmetric, so I can write whichever order. Okay? Let's write it in an equivalent way. B of YQ minus QZ less than or equal to D of YP minus PZ. P is fixed, but Q is arbitrary. I cannot take Q equals 0 because prices are strictly positive. But I will take first Q equal twice P and then Q equal 1/2 P. So if I take Q equal twice P, replace Q by 2P here, and remember that D is superlinear. So it's positively homogeneous of degree 1. So the 2 would come out here, the same here. So I would get, after putting 2 in front of this expression, I have the same expression but with a coefficient 2, which means that this expression is less than or equal to 0. Do you agree? I mean, twice this right-hand side is less than or equal to the right-hand side. So the right-hand side is less than or equal to 0. But now, as I said, I cannot take Q equal 0, but I can take Q equal 1/2 P. And then in the same way as 2 was a common factor, it came out because of positive homogeneity of D, etc. Now it's the same but with 1/2. So now I get that 1/2, the right-hand side, is less than or equal to the right-hand side, which means that the right-hand side is non-negative. Do you agree? So we have equality. Now, I consider f of z. Do I have the right to consider f of z? F is defined only on the non-negative orthant, and z appeared as a supergradient. I know nothing about the signs of the components, but in fact I know, because d as a function of p is non-decreasing. In other words, now if you look at this expression, in fact we already know that the right-hand side is equal to 0. Okay, but this is not a problem. Then consider any q and multiply it with an arbitrarily large lambda, or let's say, no, it's better to say the following. Consider the vector for I from 1 to n. Consider the unit vector I. And lambda positive. And I am going to consider q equal p plus lambda ei. Okay? Is this correct? No, even simpler. I don't need to consider any lambda. So simply p plus ei. I think it works. Then this condition says that d of y p plus ei minus, there is no q minus p, so I simply take ei. I thought there was q minus p. Then, but ei I cannot take because it has to have all components positive. Okay, so I take q equal, let's say, epsilon, the sum of all the ej's, plus ei. Okay, I think this is going to work. Then, this condition says that the y, this particular q, call it q epsilon I or whatever, q I epsilon, minus this q, which is epsilon, sum of ej times z is the sum of the components of z, plus ei times z is the ith component of z. and this is greater than or equal to 0. Okay? The function d takes only non-negative values. Then I have that zeta plus epsilon, etc., is greater than or equal to 0. Epsilon is an arbitrary positive number. Let it go to 0. Then this expression disappears. So we get zeta greater than or equal to 0. So this proves that the vector Z has non-negative components. Do you agree? So I can consider it to be an input vector. Belongs to R plus n. Is this clear? Which expression? Yeah. In fact, okay, let's do it better. I mean, I'm trying to keep the statement, but maybe I will eventually have to erase it. So, what we have is that this expression is less than or equal to that, which is 0, as we saw, for every q. Okay? And now I want to use this property to prove that all the components of Z are non-negative. So I consider one component I, the corresponding unit vector EI, and epsilon positive. And then I consider the vector which I call QI epsilon, which was epsilon times the sum of the EIs, which is strictly positive. It's the vector with components epsilon, epsilon, epsilon everywhere, plus, or let's write J, because we have fixed I, plus EI. Then this inequality, which I can write in the way QZ greater than or equal to dyk, yq, for every q, I apply this to that particular q. Okay, and what I get here is epsilon times, when I make the inner product, the sum of all the components of Z plus the ith component of Z. And this is greater than or equal to this expression for that particular Q. But this expression is non-negative. So this is greater than or equal to 0. And this is true for every epsilon. Then if you let epsilon go to 0 plus, then you get Zi greater than or equal to 0. Is this correct? Yes? Well, so now that I know that Z is in R plus n, has non-negative components, I am allowed to consider f of z. F was only defined on the non-negative orthon. So without knowing that it is non-negative, I don't have the right to write P of x, P of f of z. But now, look at this expression, which we have just used. It says that for that particular z, this y here satisfies all these conditions. So it must be less than or equal to the maximum of all those y's. So this particular y should be less than or equal to f of z. Do you agree? And now, because of this, the cost of producing y under the price is P is less than or equal to Pz in view of the definition of the cost function. I can produce y with z. This is what I am saying here. Then the minimum cost is smaller than the one obtained by producing y by means of z. Okay? It's just using this definition. Oh, but Pz was equal to d of yp. Finished. Okay, we had the opposite inequality. So we have equality. So the conclusion is that every function satisfying all these conditions can be interpreted as a cost function because I have constructed a production function which induces that function as its associated cost function. So these properties here are characteristic of cost functions. Every cost function satisfies all these properties. Every function satisfying all these properties is a cost function associated to some production function, which is not unique. But I was able to produce one. If you have a production function, but you didn't tell me, but you simply told me the cost function. Since your cost function satisfies all these properties, then I can apply this construction, and I will never be able of obtaining your f, your production function, but I would obtain an equivalent f, another production function which produces the same effects as yours in terms of minimal costs. Okay? That is the idea. So if you want, now I can try to make an exercise to illustrate this result. We can consider Cobb-Douglas functions. So we saw that a Cobb-Douglas function is a function of this type. Defined on the non-negative orthon, and A and alpha I are positive constants. Okay. By the way, this function is very nice. It has the properties that we saw that the production function we constructed in that proof has all these properties. It's quasi-concave, as Professor Mishra told us. Then it's non-decreasing, it's continuous. Fantastic. Okay? And we computed the cost function corresponding to this f. And after some complicated computations, where do I have this expression? Yes, I have it here. Then we saw that, okay, P is P1, Pn. The cost function is alpha times y over alpha to the power 1 over alpha product of pi into alpha I to the power alpha I into alpha, where alpha is the sum of the alpha i's. We could try to apply the preceding construction. I mean, this is a cost function, so it satisfies all these properties. So if I define f as in the previous proof, then that f will produce this cost function. It doesn't mean that it would be the Cobb-Douglas function. It will be, in principle, an equivalent production function, equivalent in the sense that it would induce the same cost function. Let's do this construction, but with such an abstract formulation, it would be a nightmare. So let's just, because it's in order to, in practice one does not do like this. One uses Shephard lemma, which we will see later. Okay? So to make the direct computations in general would be too complicated. So let's just consider a very particular case, so we can manage the computations more easily. Although in the end, I will need your help for a very elementary computation, which I have done many times, but now in the room before coming, I didn't understand my computation. I mean, it's very elementary, it's for high school children, even less, okay? But then, I really will need your help. So, to make things easy, I'm going to consider just two inputs, A equal to 1, alpha 1 equal 1/2, and alpha 2 power 1/3. Then, well, it's a pity that I erased the expression for the cost function, but if probably you have it there, then the cost function of y P1, P2 according to the general expression I just erased, is alpha, the sum of the alpha i's, 1/2 plus 1/3, which is 5 into 6, times y over a now is equal to 1. So y to the power 1 over alpha, this is alpha, 5 over 6, so 6 over 5. And then P1 divided by alpha 1. So divided by 1/2 means twice P1. To the power alpha 1 divided by alpha. Alpha 1 is 1/2. Alpha is 5 over 6. So this is 3 over 5. And the same with P2. P2 was P2 divided by alpha 2. So divided by 1/3, so means 3 P2. And the exponent here is alpha 2 divided by alpha, which is 1/3 divided by 5/6, so 2 over 5. Okay? This is the cost function in this particular case, according to the general formula we saw. Then I erase this production function. I want to compute, but remember it. I am going to produce an equivalent production function, which induces this cost function. Okay? And this equivalent production function, according to the proof we have just seen, would be given by f of x1, x2 equal to the maximum over y in R plus. So now C is our D there. I mean, you have given me this function. You have not told me that it is the cost function associated with a Cobb-Douglas. You just give me this expression. And then I say, oh, nice. This function C satisfies all the conditions. Then if I compute a function f of x but by that formula, then the cost function it will induce will be that function. But it doesn't mean, let me insist, that this will be the Cobb-Douglas function. So the condition in this definition now it is C of y P1, P2 but in order not to write so much, I write already the expression of C, which plays the role of D. Less than or equal to P1 x1 plus P2x2. So that's the general expression we used in the previous proof, but in this particular case, when D is this function. So I have to compute this maximum. So I have to maximize over y. Okay? So let us consider this maximization problem. So let me move all the constants into one single constant, which I will call k, which will be 5 over 6, 2 to the power 3 over 5, and 3 to the power 2 over 5. Okay. So which can be written C, because C is 2 times 3, so 2 to the power 3, 5 divided by 2 is 2 to the power minus 2 over 5, and 3 to the power 2 over 5 divided by 3 will be 3 to the power minus 3 over 5. So this is the value of k. So we have the problem we have to solve is k y to the power 6 over 5 P1 to the power 3 over 5 P2 to the power 2 over 5 less than or equal to P1x1 plus P2x2. This is incomplete. This is for every P1, P2. Okay? That was the definition. So I have to maximize y under infinitely many constraints. Because there is one constraint for each price vector P1, P2. So this means k to the power y 6 over 5 less than or equal to, I divide the right hand side by these powers of P1. So P1 divided by P1 to the 3/5 is P1 to the 2/5 with negative exponent. And here we have also 2 over 5. So this gives P2 over P1 2 over 5 x1 plus the same here, P2 divided by P2 to the power 2 over 5 is P2 to the power minus 3/5, which together with this P1 would give, but I don't think it is correct. So P1, no, here is P1 over P2. And here is P2 over P1 to the power 3 into 5 times x2. Is this correct? For every p. So well, we have one constraint for every pair in R++2, but this pair appears always in the form P1 over P2 or P2 over P1. So I can consider just one variable, which I will denote by lambda. So now the constraints are parameterized by just one real number instead of by two. Well, now I think it's time to erase all this. So what we have to solve is to maximize y under the constraint ky 6 over 5 less than or equal to lambda to the power 2 over 5 x1 plus 1 over lambda so lambda to the power minus 3 over 5 x2 for every positive lambda. Okay? So, for every positive lambda means that the left-hand side must be less than or equal to the minimum value of the right-hand side, the minimum overall lambda, assuming that such a minimum is attained. I'm going to make still a new change of variable. I'm going to call mu equal to this coefficient. It simplifies things. And so now our last formulation is mu x1 plus, so what is lambda to the minus 3/5, because lambda is mu to 5 over 2 and this to the power minus 3/5, so it's mu to the power minus 3/2, if I am not wrong. And this is for every mu, strictly positive. Now we have it ready to minimize the right-hand side with respect to mu. And this is a nice minimization problem because the right-hand side, as a function of mu, is convex. Okay? The second derivative is positive. So if I apply Fermat rule, then I will have a global minimum. So let's do this. I take the derivative with respect to mu. And I solve for mu. This is the optimal mu in the right-hand side, okay? Because our function is convex, every stationary point is a global minimum. Then mu is I don't have it here, okay. It's 1 over x2, but there is a minus here, and 2/3. So if I am not wrong, it should be, but I will be wrong for sure because I'm very bad on these computations. So I move the 2 here, and so I get 2x1 over 3x2 to the power minus 2 over 5. Is this correct? This is correct, but again we have to be careful because x1 and x2 are not negative, they may be 0, and I am divided by x2. So I have to consider separately the case when x2 is 0. But if x2 is 0, then since everything here is positive, okay, this simply implies that the maximum y is equal to 0. Because I can take P1 as small as necessary. Okay, and then here I get a number very close to 0, but P2, I don't play with P2. Okay, or I make P2 go to plus infinity. What is the correct argument? Yes, if x2 is 0, this term disappears. Then I can make P1 as small as I like for our given x1. And then I would have this less than or equal to an arbitrarily small number, which means that this must be equal to 0, so y would be equal to 0. So I have to consider separately the case when either x1 or x2 are maybe 0. And in that case, f of let's say 0x2 or f of x1 0 would be equal to 0. This can be considered separately without all these computations. Okay, so this is mu. And then all these conditions reduce to one condition. Less than or equal to the minimum of these values. And the minimum of these values is attained for this particular mu. So this means 2x1 divided by 3x2 minus 2 over 5 times x1 plus this mu to the power minus 3 halves, which gives 3 over 5 as the exponent. x2. Okay? So now I had the problems I told you, but I think I have solved it meanwhile. So I think I will not need your help. Then we have to solve for y. But let's write this maybe in a better way. So here I have x1. So let's write 2/3 over minus 2 over 5, x1 to the power 1 minus 2 over 5, so which is x1 3 over 5, and then x2 2 over 5. And here 2/3. Three over 5, x1 3 over 5 times x2 1 minus 3 over 5, which means 2 over 5. Fantastic, because it's the same as here. So I get 2/3 to the power minus 2, 5, plus again 2/3 to the power 3 over 5, x1 3 over 5, x2 2 over 5. So y to the power 6 over 5 should be less than or equal to that number divided by k. What was k? K was this. So I have to put 1 over k in the right hand side. So 6 over 5 and then 2 to the power 2 over 5 times 3 to the power 3 over 5. Times all that. And then what do we get? 6 over 5. 2 to the power 2 over 5 times 2 to the power minus 2 over 5 is 1. 3 to the power 3 over 5 divided by 3 to the power minus 2 over 5 is 3. Here. No, is it correct? Yes. I mean, 2 to the power 2 over 5 multiplied with this power of 2 gives 2. And this power of 3 cancels out. So it's wonderful. I don't like this 6. This 6 must be a mistake. But we have here 5 over 6. Was it correct? Is 5 over 6 here? Yes, because it was the sum of the alphas. But it should disappear sometime. No, because it's 5. The 6 disappeared here. But I was using this expression instead of that one. So there is no 6. Should be 1. Three plus 2 makes 5, divided by 5 is 1. So y to the power 6 over 5 should be less than or equal to x1 to the power 3/5 and times x2 to the power 2/5. Then I solve for y, and I get that this is less than or equal to this to the power 5 over 6, which gives x1 over 1/2 times x2 over 1 over 2/3. And we are maximizing y. So we are considering the maximum y satisfying all that, which eventually becomes the maximum y satisfying this inequality. The maximum y is our production function at x1, x2. No, it's so 2, 5, 5, 6 is 1/3. Okay? So this production function induces that cost function, which one was the one that you obtained with this function. I was not expecting to find your Cobb-Douglas function. Well, it's a lie. I was expecting, I knew that I would obtain this function. Why? Not because I have done this exercise on other occasions, but because the function you used is regular. So what we are going to see, maybe tomorrow, no, now it's time to finish. What we are going to see tomorrow is that when you give me a regular production function like Cobb-Douglas, quasi-concave, non-decreasing, upper semi-continuous, then this construction from its associated cost function produces the function you used. In other words, there may be many production functions inducing the same cost function, but there is only one that has all the good properties. One with the good properties can be recovered. So, from the cost function. So I cannot have two different regular f inducing the same cost function. Okay? This is the unique production function. We are going to see this in detail. This is the unique production function with the good properties. Quasi-concave, non-decreasing, and upper semi-continuous. Okay? So I knew that I would obtain a function with these properties because of the theorem. But in principle, I didn't know that I would obtain your Cobb-Douglas. But after I will tell you tomorrow the theorem that says that if the initial function has all the good properties, then this construction produces that function, not any other. And that regular function is the largest production function that induces that cost function, if you remember how we proceeded. I asked you this morning, are you able to solve this equation for f? You said no. Well, you said nothing, but I knew that it was not the case, because nobody can. But I told you what, the most I can say about f of x is that it is less than or equal to this expression. And then we tried with that expression. So every production function that produces the cost function is less than or equal to that expression. So that expression is the largest production function, which induces the given cost function. It's the largest, it's regular, it's the only regular production function. Okay, so we'll continue tomorrow.
Do you have any questions? We can discuss over tea.
Over?
Over tea.
Not me.
But you can discuss.
I can discuss, but not with tea.
We have 5 minutes break and then.
Because now you have to, okay.